guys, hey. Yeah, hope you're all doing good out there. It's time to move on to finding the extreme values of functions. We're going to figure out how big and how small a function can be just using the derivative. Take care of each other out there now. We're now going to talk about how to find extrema, which mean the maximum and minimum values of functions. Now, what does that mean? The maximum value of a function f of x, sometimes also called the global maximum or the absolute maximum, is some output of the function, something that the function outputs for some input c, for which f of c is bigger than or equal to f of x for all other inputs x under consideration. In other words, that's just a fancy way of saying it's the biggest value that the function outputs. It's the biggest value, the maximum value. Similarly, the minimum value of f of x, also called the global minimum or the absolute minimum, is an output of the function f of c for which f of c is less than or equal to f of x for all other inputs x. It's the smallest value that the function outputs. So let's look at the graph of a function. Here we go. Here's some f of x. What are its maximum and minimum values? Remember, the outputs are in the y direction. That's the vertical direction. So for the maximum, we see that this point right here is the largest, the highest value that the function obtains. So the maximum value is 10. That's the height here in the y direction. It's 10. And in this example, it occurs at the input x equals 8. What's the minimum value? The minimum value, that's the smallest number output by the function, that happens right down here. Notice that this is close, this is in the running, but this is a little bit lower. That point right there, 3, is the minimum value that the function outputs. That happens at x equals 4. Okay, so in various applications of mathematics, you have some function. Maybe it tells you how much money you're going to make based on some parameters, or how fast your spaceship is going to go, whatever it is, and you want to figure out the largest and the smallest that function outputs in order to achieve that situation. So we want to find maximum and minimum values. How are we going to do that? So we're going to establish a procedure here where, supposing we don't have this picture, we don't know which is the biggest and smallest values, what we're going to do is we're going to analyze all of these points where the function turns around. These are called the local max and local mins, the local maximum and the local minimum. And technically, if the function is also defined on an interval, like this one is defined from 1 to 9, we're also going to look at just the values at the ends of the interval. And then we're just going to compare all of the outputs of the function at those points, see which is bigger, see which is smaller. So let's first get at the idea of the local maxima of a function. So here we go. A local maximum of f of x is an output f of c such that f of c, that output, is bigger than or equal to f of x, not for all inputs x, but for all inputs x in some interval containing c. I don't mean a specific one, I just mean you can restrict attention, you can find some interval where it's the biggest thing around. Okay, so how does that work in our example? Well, if I restrict attention around the point 2, if I put on some blinders like this, all of a sudden that rise up, that mountain peak, it's the tallest point around. It is a maximum if I restrict attention to this interval around 2. That's what I mean by some interval. You can find some interval where it is the maximum value. So restricting attention to this interval of inputs we see that that point right there is a local maximum because for those inputs it's bigger than or equal to all of them. So here I'm going to show you the local maxima that there is one. There's another one right here because it turns around and goes down, right? So locally, in some interval near that point, it's larger than f of x for all inputs x in that interval. And the global maximum that we found is also a local maximum. That's a general fact. In general, a global maximum will be a local maximum as well. Okay, so that's the idea of a local maximum. What's a local minimum? It's the same idea. A local minimum of f of x is some output f of c, which has the property such that f of c is less than or equal to f of x for all inputs x in some interval containing c. So, for example, on the graph here, if I restrict attention to this little interval around 6, whatever it is, I just need to find 1 to make this work. For those red points on the graph, this little dip here, the bottom of the valley, is the smallest thing around. That f of c is less than or equal to f of x for all x in the red interval. So that's a local minimum. What are all the local minima on this graph? Well, there's that one we just found. Here's another one, right? As you dip down, that'll be a minimum point for its neighborhood, so to speak, for the points near it. And then in this case, the endpoints are also local minima, because if you restrict attention near those points, just for inputs of the function, they're smaller than everything else. So they also count as local minima.
A 9-year-old boy talking to his father. Daddy, what is politics? The boy asks a pertinent question. Father had to think now to give he a pertinent answer. What is politics?
So here's a strategy to find the maximum and minimum values of a function. The first step is to identify all local maxima and local minima. As we saw in that picture in the last example, the global maximum and the global minimum will be somewhere amongst the local maxima and the local minima. All right. Now we're going to evaluate the function at those points. So we're going to evaluate f of x at those points at the corresponding x values. And then technically, if we're restricting attention to some interval, we should also evaluate the function at the endpoints of the interval. So if the interval, if the domain of the function is just some small compact interval, we should also evaluate at the endpoints of the interval. So if f of x is only defined on an interval. If it's defined on the entire real number line, then we don't need to worry about that. And then finally, the third step is just to compare. See which is the biggest, which is the smallest. That is the program. Okay, so we're going to implement this strategy, and as you'll see, it's all about step one. How do we identify the local maxima and the local minimum?
Father, haughty brains, he says, son, let me put it this way. I have to provide for you. So I am the capitalist, You are the people. Your mother does keep the money. She is the government. The babysitter is the working class, and your baby brother is the future. You understand? Well, the boy couldn't put that jigsaw puzzle together. He say, I think so. He gone to bed and he's sleeping. While he's sleeping,
Let's just look at a little picture here of a local maximum. So the function might do some other stuff elsewhere, but here we have a picture of what a local maximum looks like. All right, and let's draw an x-axis down here. So there's a local maximum here at C. We want to figure out what behavior of the function we can identify that will imply that we have a local maximum. All right, think about the tangent line to the graph of this function. The tangent line here to the left of the local maximum, it has positive slope. All right, so here we have positive slope because the function's increasing. That means that the derivative here is positive. On the other side of the local maximum, if we look at a tangent line there, that's decreasing. We have negative slope at those points. The derivative is negative. And what happens right at that point, right at the top of the mountain, at the local maximum? Well, at that point, the tangent line would be perfectly horizontal, right? So what we're observing is that the local maximum occurs exactly at that point where the tangent line is horizontal. That's the point where the derivative transitions from being positive to negative. So this local maximum, it's occurring right at that point where the derivative is 0. Okay, so let's write down that observation. The local max occurs at an x value, which would be the C here in the picture, where the derivative is 0, because that tangent line's got to be horizontal. It's got to have 0 slope. And if you think about it, the same thing will be true of a local minimum. It's just that we go from decreasing to increasing. So if we draw the analogous picture with the local minimum occurring at some x value C, then we see that that's exactly the point where here the derivative is negative, negative slope, function's decreasing. Here the derivative is positive, positive slope, increasing. And then right there, smack dab in the middle, where we have the local minimum, the tangent line would be flat. The derivative is 0 at that point. At C, the derivative is 0. So the same statement is also true of the local minimum. All right, the local maximum occurs at an x value where the derivative is 0, and then the same thing is true of a local minimum. A local minimum occurs at some x value C where the derivative is 0. Okay, so we're going to give ourselves a name for these points where the derivative is 0, because that's the whole strategy. That's the whole point to the first step. That's how we find local maxima and local minima. So we call these critical points. We call them critical values. The corresponding point in the plane is the critical point. So a critical value of f of x is simply an x value, some C, where the derivative is 0. As we've seen from these pictures, local maxima and local minima, they occur at critical values. Okay. they occur where the derivative is 0. What's the upshot? The upshot is that in that first step to finding the overall maxima and minima of a function, to find the local maxima and minima, we first find where the derivative of the function is equal to 0, i.e. we find the critical values.
In the morning, he get up, they having breakfast. He said, Dad, I think I know what is politics. He said, good. Tell me in your own small way, what is politics? He said, well, Dad, it's something like this.
Never gonna give you up, never gonna let you down, never gonna run around and desert you, never gonna make you cry, never gonna say goodbye, never gonna tell a lie and hurt you.
We're going to find the maximum and minimum values of the function f of x equals x cubed minus 9x squared plus 15x plus 15 on the interval from 0 to 6. So we only accept x values in between 0 and 6 in this discussion. So the first step is to find the local maxima and minima, and in fact we're going to do something more general. What we're going to do is we're going to find the critical values. Since we saw that all of the local maxima and local minima occur at critical values, it suffices to find the critical values. That just means that we need to figure out where the derivative is 0. We need to solve the equation f prime of x equals 0 for x. That'll tell us what the critical values are. Okay, well, what's the derivative of this function? This is a polynomial. Derivatives of polynomials are easy enough. We just use the power rule on each piece. So term by term, bringing the exponent down, multiplying it by the coefficient in front, and then subtracting 1 from the exponent, we see that the derivative is 3x squared minus 18x plus 15. And now we set it equal to 0, and we need to solve for x. Well, we could use the quadratic formula at this point to find the solutions. But we can also just do it by hand by factoring. Let's do that. So I can factor out a common factor of 3. And then x squared minus 6x plus 5, well, that factors as x minus 1 times x minus 5, right? So that means that the critical values, the x values where the derivative is 0, are the x values that make these terms 0. That's x equals 1 and x equals 5. Okay, great. And now those critical values, we don't immediately know if they're local maxima or local minima, but the point is that if there are any local maxima or local minima, they're going to be included in this list. So we've covered all of our bases. Okay, the second step is to evaluate the function that we got, f of x, first at these critical values. So let's plug in 1 into the function. If you plug 1 into this function, remember the function is x cubed minus 9x squared plus 15x plus 15. If you plug that into the function, you'll end up getting 22. I won't show you the arithmetic. Either do it by hand or use a calculator, but that's what you'll end up getting. If you plug in 5, you'll get minus 10. So those are the values that the function outputs at these critical values. Okay, that isn't the only place where we need to evaluate the function, we also need to evaluate the function at the endpoints of the interval where we're considering the function. The overall maximum or minimum could occur at those endpoints, so we also need to take that into consideration. If you plug 0 into the function, you'll get 15, and if you plug 6 into the function, you end up getting -3. Okay, so we've evaluated the function at the critical values and at the endpoints of the interval. Now there's one final step to discover the overall maximum and minimum, and that is to compare. We look at these outputs and we say, hey, which is biggest, which is smallest? All right, well, the biggest value on this list is 22. That's the largest output that I see there. And so that's going to be the maximum. It's the biggest number on this list. What's the smallest value on this list? That's -10. So that'll be the minimum. So after comparing, we see that this function, which again was x cubed minus 9x squared plus 15x plus 15, has a maximum value of 22, and that's achieved at x equals 1, and a minimum value of -10, and that's achieved at the input x equals 5. Okay, great. So that completely solves the problem of the maximum and minimum outputs of this function. Okay, I got a follow-up question. What if we looked at the same function but on a different interval? Suppose that instead we looked at the interval from 0 to 8. Okay, how would this process change? Well, going back to the beginning, the first step, finding the critical values, the points where the derivative is 0, that would be exactly the same. That's always the same. Now, if any of these critical points, those critical values, were outside of that interval from 0 to 8, we'd throw them out. They wouldn't be under consideration. But these critical values, they were both in the interval from 0 to 6. They're both in the interval from 0 to 8, so nothing changes. The next step would be the same. We would evaluate the function at those critical values. The only thing different here would be the evaluation at the endpoints. So we have that list of values. The only other thing we need to look at is the value at that new endpoint 8. So we only need to evaluate f of x at the new endpoint. That's the only difference in the process. Well, if you pull out a calculator and plug in 8, or you do it by hand, you'll end up getting 71. Alright, so now in the third step, when we compare, this 71 would now have to be compared to these other numbers, 22 minus 10, 15 minus 3. Well, 71's bigger than 22, right? So the only thing that would change would be that in this case, 71 is the new maximum. So looking at the interval from 0 to 8, f of x has a max value, this time of 71, and that's at x equals 8, and the minimum value is the same. So it has a minimum value, again, of -10, and that happens at x equals 5. Here, let me show you. We can see that our answer to this problem is correct by graphing the function on Desmos. Check it out. So here's the cubic function that we just discussed, and the critical values, that's where the derivative is 0, where the tangent line is horizontal, That occurs here at x equals 1 and x equals 5. You can see the outputs of the function that we calculated before. And indeed, if you look at the graph, the tangent line would be horizontal there. Well, what about the overall maximum and minimum? Remember, we were only considering x values from 0 to 6. I can actually make Desmos show that. So I can say if x is in between 0 and 6, doesn't really matter if these are strict or less than or equal to inequalities for the purposes of Desmos. I'll have to use curly brackets to do that. Then it'll show me only the parts of the function that lie in between 0 and 6. And indeed, we then see that the maximum and minimum values are precisely 22 and minus 10, occurring at those two critical values where the function is turning around. Okay, and in the second part of the problem, we considered the same question where we were only looking at the x values in between 0 and 8. In this case, the answer is different. As we saw, we have the same two critical values. Minus 10 is still the minimum, as we can see from the graph, but 22 is no longer the maximum. To find the maximum, we have to go way up here to this point at the edge. It says it's undefined. That's because I've used less than instead of less than or equal to. That output there is indeed 71, what we computed. So we see that's the biggest thing around. That's the biggest value on the graph, confirming the calculation that we did by hand.